complex matrix of order, square matrices of order n on the complex numbers. And I can define the kernel omega tensor, the identity on the matrix n, as a kernel from this. In our case, the kernel map, the elements of the kernel map elements of this algebra into itself. Now, I can and this algebra can be identified with the n by n matrices with coefficient in the algebra A. Now, this is it. Now, what I say in complete positivity is better to, since this kernel is a matrix, this kernel, independently of this kernel already I can consider as an element of this algebra, okay? Because it is a matrix. Because omega is a matrix. So it belongs to the matrix with coefficient in A, and this matrix algebra is isomorphic to this. Okay.
MDC. So the omega is.
Indeed. MD. Okay. MD. Okay. So this matrix is an element in MD. Now, suppose that I go still further and I consider now matrices of order n on MD. Okay. Then this will be identified to and an element omega in MD is identified in this method. Omega, which is in MD, will go into omega tensor the identity of N. And now I require that we call this omega n. Omega we already gave name to omega n. So let us call this omega hat n, which is the ampliation of the natural ampliation of the kernel. I say that the kernel is completely positive definite if I have omega is completely positive definite if for each n and for each y1 ym belonging to mn of I have that the analog relation for omega hat n. But now jk go from 1 to n. Because now this is an n by n matrix with the coefficient here, okay? Because also this is a star algebra, so also here there is a notion of positivity. In this sense, as I said last time, this is a little bit improvised definition because there is no. The standard definition is a complete positivity in star algebras, in a C-star algebra, in von Neumann algebra. But the theory of completely positive maps in more general star algebra is not being developed. Okay. However, this is a plausible definition and also suggests a possibility of generalization. Okay.
So each of omega.
In fact, the complete positivity I insisted because, in my opinion, this problem to develop a theory of a completely positive map on star algebra is an interesting problem in operator theory by itself. However, we will never use the complete positivity of this scalar. In our reconstruction theorem, we only use the positivity, which is this. Okay? The complete positivity is, you should look as a kind of open problem that can be kept in mind. Okay? Because this property, since we have an explicit form of this kernel, we can deduce, we can how to say, remark that in fact it has a much stronger positive property than positivity. So the constraints. So in fact, let's say this is so this is a matrix with real coefficients and which is positive definite. Hermitian comes from the symmetry. It's positive definite and Hermitian, which means symmetric in this case because it's real coefficient. So simply the jk coefficient is equal to kj coefficient. Okay. And now the omega n have an important constraint that the kernel, the imaginary part of the omega tilde n plus 1, I take n plus 1 because 1 is separate, 1 is very special due to the very special fact that V0 is dimension 1. The imaginary part of the kernel n plus 1 coefficient jk is equal. By the way, remember that this is, by definition, by our definition, this is nothing but the imaginary part of a minus j, a plus j, restricted to n. And n plus 1 means that this kernel uniquely defines the scalar product in the n+1 space.
So that will be AK plus. AJ minus AK plus.
KKK. Yes, thank you. Okay. So when I restrict this, I have the imaginary kernel. This is a definition, but this is the new information. This is the kernel, imaginary part of the kernel with the flipped plus and minus. This is very non-trivial part. Well, I can also, they commute, restriction operator commutes with the imaginary part. So I can put whatever. Well, I at the moment I'm not saying the inductive formulation. So this is a property. First we have proved this. First we have proved just the general kernels without restrictions. And there is also the zero part, which is also KG. So you see very well from here the constraints that I was telling to you. The kernel, this kernel, which is my kernel omega tilde, is not independent from A0, because there is this relation which says that, and our point will be to transform this into an inductive constructive relation. Okay? So this is the first constraint, and the second is a linear equation which constrains the A0. So this is equation constraint 1, let us say, and constraint 2 is A0 or A. To see. So these are the two. The two constraints that we deduced from the three commutation relation. It is a theorem that you have to prove. I have written the proof in the lecture notes, that the third relation does not add constraints, fortunately. So we have only two types of, you see now the big difference with the Favard lemma. With the Favard lemma, this not only there are no relations between the alpha, but there are inside the alpha n, there are no relations between alpha n and omega n, but there are also no relations inside alpha n. But this second tells us that there are relations inside alpha n. Remember, what is alpha n? Alpha n is the restriction of A0 on the Pn. So these two relations can be written in inductive formulation, and this gives you a lot of insight. Because let us write C1 in inductive formulation. C1 in inductive formulation, you see, means that the kernel omega tilde, the imaginary part of the kernel of the coefficient jk. So sorry, here I left omega n plus 1. I should only put the omega jk, because I didn't restrict. Now I restrict. You correct at least, because I put n plus 1, but this is a relation between operator on the big space. Now we restrict, because see this identity, this operator is gradation preserved. So the identity is true. In fact, if I have two operators on a space with a gradation, the two operators are equal if and only if their restriction on each subspace of the gradation are equal, because it's obvious the gradation are independent. So now we restrict these two on the n, and from omega jk restricted to n, we get what we have called omega n plus 1. And this is equal to the restriction of this imaginary part to n. Now remember, a minus, the restriction to this, here the big difference is that here there is first a plus and then a minus. But here there is first a minus and then a plus. Then this means that if I act with this operator on n, I get something that is in n minus 1. And so this operator will act in n minus 1. So this is j acting on n, and this will be k acting on n minus. And this is the imaginary part. Remember, imaginary part of an operator is an operator, let us call A, is A minus A star divided by 2i. And similarly, A0 is gradation preserved. And so this is simply the imaginary part of A0 k restricted to n, A0 j restricted to n. Look at the difference. One decreases and one is gradation preserved. So you now interpret, you see, but here, this object, when I will make explicit the restriction, I will find that this object is a daga k restricted to n, but this will give me a minus j restricted to n plus 1. And so you see, you guess the induction relation. I will get the information on the restriction on the n plus 1 space if I give the restriction on the n space. Okay. You see, here a daga is on n minus 1, and here is on n. However, and from the quantum decomposition, you see Xj, when you write it in inductive form, you write as a daga j equals xj minus a0j minus a minus j. And this is inductive, because it tells you that if I know the restriction on J on N, A0 on N, and A minus on N, automatically I know A daga on N. But if I know A daga on N, I know as a vector space Pn plus 1. And since such a J is purely algebraic, completely independent of any state, this allows you to go to do the induction. Because this becomes, when you write it inductively, A daga J restricted to N will be given by Xj restricted to N, A0 J restricted to N minus A minus J restricted to N. And so you get the operator that you need here.
Okay. So the idea is to go algebraically so that it's independent of what the final state we arrive at.
Huh?
The idea is to go
Exactly.
algebraically so that it's independent of the final state we arrive at.
Yes.
So we want to reconstruct.
The idea is to begin from now. Now we have shown that once we have the gradation, what have we done? Let us translate summarize what we have done up to now. Essentially, we have proved the first part of the theorem, and then we will prove the converse. We have proved that if we give the gradation, which means, what does it mean to give the gradation? Means to give the decomposition of P as the decomposition of P considered as a Hilbert space is, in fact, so let us write P0 to remember that now we are at Hilbert space 11. And we have constructed, given the state, on P, we have constructed what we called the interacting Fock space. Interacting Fock space is the gradation of the Pn, each with its product, the sum is orthogonal and direct is vector space, because each Pn is made of monic polynomials. Okay? And then we have also constructed the creation operator. So we have a certain interacting Fock space. Remember our notion of interacting Fock space. An interacting Fock space